what we're gonna do, just like the drill that we did before, is by saying that because M internal is negative EI times Y double prime, and by rearranging all these terms, we're gonna have this result, which is Y double prime plus P over EI times Y equals to WX squared over 2 minus WL over 2 times X. Now, the general solution, which is the expression of Y of X, has two parts. One is particular, so this will leave you to the YP. This will leave you to the YC, complementary, right? The total solution is the summation of these two. And that means for Y of X, we know that the complementary solution, Y equals to YC plus YP. So we have two parts. The first one we are very familiar with because that's the case when it's 0, which means that there's no loading. And you already know the expression of this one because we have used it so many times. YC is capital A times the sine KX plus B times cosine KX. Remember, right? We have been doing this so many times. I think that you're not going to forget about this expression. The complementary solution, which means that is the case of what we call Euler buckling. And of course, if it's not clear to you, what is K? K is the square root of P over EI. Now, for particular solution, particular solution carries this form. If you have polynomials as the non-zero term, the particular solution will carry the same form with only one order different, which means it has to be continuous. And if you look at the polynomials, we have this second order, we have the first order, right? But we don't have the zeroth order. But in the general form of your particular solution, you should consider a continuous series, which is from second order to the first order to the zeroth order. That means the particular solution, if for the coefficients is C1 times x squared plus C2 times x plus C3. It's like this. Now what we have to do is just to plug in to determine this. And if you have a YP in this form, well, you will know that Y prime of P, that's the first order derivative. And that equals to 2C1 times X plus C2. And the second order derivative would just be 2C1, right? That we know. And then, how do you find out the coefficients for the C1, C2, or C3? And from differential equation, you know that you just plug in the expression of YP and YP double prime into the governing equation. So from the governing equation, we know that EI YP double prime, here is the case we consider only the particular solution, plus YP equals to what? You substitute the expression, plug it in into this, and you know that that equals to 2C1 plus K squared times C1x squared plus C2x plus C3. So this part here is just YP, which is 2. Picture this part like this. And your 2C1 is just this part. And then by comparing the terms, we can deduce the following. We know that C1 times K must be, of course, this whole thing equals to what? Let me complete it because we haven't really finished. And this expression equals to W over 2 times X squared minus WL over 2 times X. You can consider that it can be written this way. In other words, to find the values of C1, C2, C3, it's just to compare the terms on the right-hand side of this equation. So when you expand all these coefficients together, you put all the coefficients related to x2 and make it equal to W over 2, because the coefficient associated with x squared is just W over 2. And the coefficient associated with x is negative WL over 2. So we're going to use these coefficients to find out the values of C1 and C2. So from here, we will know that C1 times K will equal to W over 2EI. And that means C1 is W 2EI over K. And also we know C2K is negative WL over 2EI, which means that C2 is negative WL 2EI over K. Now, for the zeroth order, there's no zeroth order, right? Because in the original solution, it actually equals to plus 0. If you can think about this way, right? That means the zeroth order, there's no coefficient. That means that's another condition, which means the coefficients on the right-hand side about C1 and C2 and C3, the zeroth order term must be 0. That leads to this expression, which is 2C1 plus C3 times K squared must be 0 because there's no zeroth order term. So this 0 is what? This 0 is this 0 here. Now we're going to use this condition to determine coefficient C3. So from here, we know the expression of C1, of course you can find the expression of C3. And that will leave us expression of C3. C3 equals to negative 2C1 over K squared, which is negative W over EI over K quadruple. So this technique is what we call comparison of coefficients.
Professor.
Yeah.
When you set up the equations for finding the values of C1 and C2, shouldn't K be squared in each of those?
Which one?
When you get C1K is equal to W over 2EI, shouldn't it be K squared because you multiply K squared?
Wait. Yes, you're right. You're right. Why I forgot about all these squares here? It's weird. Thank you. Okay. So from here, we found the coefficients for the particular solution. Now let's come back to the complementary solution. So how do we find the coefficients for A and B, which is the one that we have here too, right? Now we can look at step 3. How do we do that? We use boundary conditions. And so for the boundary conditions, what do we know? This at the support A is a hinge support, so we know that there's no deflection. That's written as y of 0 is 0, right? And we also know that there's no deflection at what? At the other end, which is support 2. That means y at x equals L must also be 0. Because this is symmetric loading, we also know that at the midspan, the slope must be 0. Why? Because of the kinematic admissible deformation profile that we consider. Therefore, we know that, and right here, at midspan here, the deflection must be level to the x-axis. Mathematically, we can write this as y prime at L over 2 must be 0. Right? Now, of course, some of you may wonder that, Professor, should I continue using the force boundary condition? Because so far we only use displacement boundary condition, right? The zeroth order and the first order, they are force displacement boundary condition. Should we use force boundary conditions? Well, depending on the number of unknowns you have, if you use a force order differential equation approach, then you have to continue exploring the force boundary condition. However, if you use second order differential equation approach, you only have 2 unknowns. You have 3 conditions. So you know that you have enough conditions more than unknowns. You don't need to continue writing down the force boundary condition. You can stop here and start plugging in the values. So that's will lead to the results. And you just plug in this, and you can find the expression of A and B. So first, the expression of B is W over EI over K quadruple. And the expression of A is W over EI quadruple, K quadruple, times tangent. Okay. Now, step 4. Of course, once we have these two, so I can just write down, give you the total expression, and because you need that for your homework number 2. With these two, we can write the expression of y of x. That is this expression, W times L quadruple over 16EI over U quadruple. So what is this U here? And U is a new variable we're going to define here. Let's define U to be KL over 2. That's it. Because we're going to use a lot of KL over 2. So why don't we just call this whole thing as U? We can simplify our writing and make sure we don't copy this expressions by mistakes. So this whole thing times tangent U times sine 2U times x over L plus cosine 2U times x over capital L and minus 1. So this is just to take the particular solution back here and no, the complementary solution back here. And the particular solution follows. That can be written as WL squared over 8EI over U squared times X times L minus X